Now let's continue our discussion on how to derive J. So before talking about J, let me set up alphabets for each variable. The radius of this cylinder will be denoted by C. The twist angle will be represented by phi, and the shear strain will be represented by gamma, and the length will be represented by L. So here for small torsional deformation, when gamma is very small, then using the relationship between the gamma and L, the arc length, arc length must be L gamma. Okay, this is the case for gamma is very small, so that tangent gamma and gamma can be approximated as equal to each other. And from here we have L gamma. From here we have C times and phi, and they must be equal to each other, right? So L gamma equals to be C phi. So gamma can be written as C times phi over L. Even though we obtained for this total length L, if we take infinitesimal and any length delta x, and if we consider twist angle within this zone, it can be satisfied as it can be written as gamma equals to be C equals to be delta phi and delta x. Okay, so please remember this for surface. Okay, so here I denoted as gamma at surface. Now, instead of considering the gamma, the shear strain at surface, we can think about shear strain inside. Okay, so here the original radius is C, but I'm taking a point with radius rho, which is the distance from the center, and the angle, the twist angle must be same as previous page. However, the shear strain at smaller diameter, this is imaginary surface, is small. Okay, so the shear strain must be function of rho, which is distance from the center. When rho goes to 0, gamma rho will be 0 because we are considering simply line at the center of the beam. Okay, so by identifying that shear strain gamma is function of rho, which is distance from the center, we can also identify that gamma will be maximum at rho equals C. Okay, so at rho equals C, gamma is C phi over L. Okay, now for any radius with rho, we can say that L times gamma, L times gamma must be same as rho times phi. Okay, so this equation must be satisfied for any rho. So if we rewrite gamma as a function of rho, it can be written as rho times phi over L. And if we identify that the maximum gamma is C times phi over L, plug in maximum gamma and get rid of C by dividing by C, then we end up having gamma equals to be rho over C gamma max. Okay, and gamma max turns out to be C times phi over L. So we can say that same is true for any pair of cross section at x1 and x2. We just take any arbitrary x1 and x2 point, and instead of phi over L, we can write down d phi dx or delta phi delta x. Okay, and if we do same kind of massage, putting C here, putting C here, we can say that gamma rho equals to be rho over C gamma max. Okay, so the shear strain must be 0 at rho is 0. Shear strain when at rho equals C, which is maximum, will be same as gamma max. And gamma max we obtained from the previous page is defined as C times phi over L. Okay, so this is what we have done. Because we have obtained the shear strain as a function of position, which is distance from the center, by using the material property that connecting shear stress and shear strain, which is shear modulus G, we can obtain shear stress tau. And shear stress tau as a function of rho must be obtained as shear modulus multiplied by shear strain gamma, which is function of rho. And if we plug in the expression for gamma, it can be written as G times rho over C gamma max. And when rho is C, tau becomes tau max, which is G times gamma max. Because when rho equals C, we can get rid of this guy as 1. Then, by identifying this, maximum tau equals to be G times C times phi over L. Okay. Now, from here, after plug in tau max expression to here, we identify that tau as a function of rho is rho over C tau max. Okay, so whether we consider shear strain, whether we consider shear stress, because they are linearly related to each other through shear modulus G, they are linear function of rho. Okay, so the biggest difference in torsional loading and axial loading is that in axial loading, we considered the entire cross-section have same normal stress wherever point you take. However, in torsional loading, shear strain and shear stress is not uniform over the entire sample. Okay, depending on the distance from the center, which is the rho, you have different shear strain and different shear stress. That's the complexity we are adding in torsional loading chapters. Okay, now if we draw cross-sectional view, so after the shear strain torsion is applied, and you take out this imaginary cross-section and draw the distribution of tau here. Then what you can see here is because tau is function of rho, tau becomes 0 and tau becomes max, and between the center and the surface, tau increases linearly. Okay, so this is the distribution of tau. Now, if you want to obtain the relationship between tau applied on this each plane, then what you have to do is you have to obtain infinitesimal torsion due to this tau. Okay, so tau, which is a force per unit area, is given as rho over C gamma max at this specific area. Okay, and to obtain this infinitesimal force dF, you have to multiply dA, and dA can be written as rho times d theta, which is this is rho times d theta, and this is d rho. Okay, so if you multiply d rho and rho times d theta, it can be dA. Now, in the place of tau, you multiply rho over C tau max. Okay, then you can write down infinitesimal torsion acting on this infinitesimal area as tau max over C rho square dA. Now, to obtain the torsion for entire plane, you have to do integral over the entire surface. Okay, so this is entire cross-section. Okay, then you can relate the torsion for entire area, which must be same as this torsion, can be written as tau max over C. You take out this constant and you leave this variable rho. Rho is function of position. If you do integral for entire cross-section, then you can make this relationship. Torsion T, maximum the shear stress tau max, and the radius C, and this interesting property. Now let's move on further. If you plug in the expression for tau max GC phi L here, then you end up with T equals to be G times shear modulus times twist angle phi divided by length L multiplied by integral entire cross-section low scale dA. If we define this entire guy as J, which we'll call as polar moment of inertia, then you end up having T equals to be G phi J over L. If you write down twist angle as a function of T L G J, it can be written as here. So after obtaining this twist angle, okay, so what you can see here is we can now obtain twist angle as a function of torsion torque, and the L, the length, and shear modulus, and J must be geometrical factor. Okay, after obtaining tau, if you plug in the expression for gamma as a function of rho and tau as a function of rho, yeah, you can obtain the relationship between gamma and rho and T and G and J for any point within the pillar, circular shaft pillar under the torsion. Okay, so after making this discussion, we found that now once we do this integral J, based on the formula which is very similar to this place formula in axial loading, we can obtain the twist angle phi. Now how about the value of J? Yeah, it must be geometry dependent, so let's try to do some integral. So for the entire circle, if you consider simple circular shaft and try to obtain J for the this circular cross section, what you do is you do this integral low scale dA, and as I told you, dA must be rho d theta multiplied by d rho. If you get confused about polar coordinate, please see it here. Okay, now if you plug in this and you do integral for theta from 0 to 2 pi, you do integral for d rho from 0 to c, and after doing this integral, you end up having J equals to be pi c fourth power divided by 2. Now instead of circular shaft, if you have a hollow circle, so you have a hole inside and you have the hollow cylinder, and the outer radius is C2, inner radius is C1. Then when performing J calculation, instead of from 0 to C, you do C1 to C2 integral, and you do integral from 0 to 2 pi for d theta. Okay, so after massaging this equation, you end up having pi over 2 C2 fourth power minus C1 fourth power. Okay, so this is how you obtain the J based on this integral. But you don't need to worry about performing the integral, because as I told you, if we consider like a square cross section or triangular cross section, we cannot rely on our assumption we made here. So because of this limitation, our chapter on torsional loading will only consider circular shaft or hollow circular shaft. That's it. Only these two cross section will satisfy those 1, 2, 3, 4 assumptions. Without satisfying those assumptions, it becomes really difficult problem to obtain the response under the torsion, and that will be beyond the scope of solid mechanics 1. Okay, so those complex problem will be handled in second semester, which is stress analysis course, or in other words, solid mechanics 2 course. Okay, and for our lecture ME231, you can only worry about circular shaft and hollow circular shaft, which is this and this, and that's it. You don't need to worry about the obtaining very complex J. This will be your answer in homework and midterm problems. So to summarize, these are the one-to-one analogy that we can make about axial and torsional loading. Axial loading, we have force, which is the external stimuli. For torsional loading, we have torsion, which is torque about the rotation axis, as the external stimuli. Okay, as a geometrical factor, we have cross-sectional area for axial loading, but we have polar moment of inertia for torsional loading, and the length is given as the same position. And because axial loading considers the response on the normal stress, we have to consider Young's modulus. Torsional loading considers the response under shear loading, we have to consider shear modulus, and we call this as material property. So given external loading, we have geometry and material property, and these will determine deformation of the material. So for axial loading, it was displacement delta. For torsional loading, it turns out to be angle of twist, and the equation looks very similar. Okay, so if we think about our thought process in axial loading, starting from force, we make a equation for stress, and from stress we make a connection to strain using normal stress normal strain relationship, and from strain we can obtain the displacement delta. And for torsional loading T, here we went in opposite direction. Starting from this twist angle, we obtain the gamma as a function of rho, purely from, I think it's middle school geometry. Okay, out of this middle school geometry and very simple kinematics, we obtain the relationship between gamma and phi, and because we have shear strain, we can obtain the shear stress as a function of rho by doing g times gamma. Okay, after obtaining shear stress tau, after doing the integral for the entire surface, we can relate tau and the torsion for entire sample. Okay, then we can obtain the tau as a function of torsion T and geometrical vector J, and we can make a connection for entire torque, shear stress, shear strain, and twist angle relationship. Okay, so these are the summary of first topic of today's lecture, and let's solve just one example problem. The example problem we're gonna solve is following. So the problem asks compute area and polar moment of inertia of following two cross sections. So first one is solid circular cross section with radius 3 cm, and second one is like a hollow circular shaft with outer radius 5 and inner radius 4. Okay, then what we can realize is because we have simple 3, 4, 5, there must be intention. Okay, so if we consider the area for number 1, it's simply pi 3 centimeter square. For second geometry, we have pi times 5 centimeter square minus 4 centimeter square, which turns out to be, due to Pythagoras theorem, it must be pi times 3 square. Okay, so in terms of cross-sectional area, number 1 and number 2 are equal to each other. However, in terms of J1 and J2, J2 must be larger because J2 is proportional to C2 fourth power minus C1 fourth power. So 5 fourth power and 4 fourth power, if you obtain this calculation, it must be quite larger than J1, which is simply proportional to 3 centimeter fourth power. Okay, so here the implication for this cross section is that number 1 and number 2, they're gonna have same response under axial loading. Okay, so if we apply like 100 Newton or 1 kilonewton for each shaft, they're gonna have same displacement delta. However, even though they have same response under axial loading, if we do apply the same torque or same torsion for number 1 and number 2, their twist angle will be different. Because this guy has higher J, the second one will deform less than the first cross section under the same torsion. Okay, so these are the conclusions that I can make about first topic of today's lecture.